Okay, so in this video, we want to start stepping up a little bit our sophistication of the things that we're going to prove using contradiction. So we're going to prove two famous theorems in mathematics. In this video, we're going to prove that there are infinitely many prime numbers. Okay, good. So again, let's just remember what we're talking about when we talk about prime numbers. So we're looking at numbers like 2, 3, 5, 7, 11, 13, 17, 19, 23, so on and so forth. These are numbers that cannot be broken down into smaller factors, right? And just want to remind you that we don't consider one to be prime for several reasons. For one, um, you can always break one down into one times itself or something like that. So it becomes a little bit um, not a good thing to involve one in this operation. Um, in any case, so here are the prime numbers. And what you should think about for a second is that, it's possible that if you get to larger and larger numbers, that eventually you can always break numbers down into smaller pieces, right? Like perhaps when you get into you just consider large enough numbers, they are such that they can always be broken down into smaller pieces. And what this theorem is saying is that that's not the case. If there's infinitely many prime numbers, then there must be prime numbers of arbitrarily large size. So our intuition that like the larger numbers get, the more likely they are to break down into smaller pieces, that's probably true. But there will always be these sort of special numbers, no matter how large you go. There'll always be these special numbers which cannot be broken down into smaller pieces. Okay, great. Now this is a famous proof that's contained in Euclid's Elements. And so it's been around for a long time. And let me give the sketch. We're going to do this by contradiction, because if you assume that the opposite, then you're saying that there's only finitely many prime numbers. And if there's only finitely many prime numbers, then again, you can work with those finitely many in a very simple way. So assume there are only finitely many prime numbers. Okay, and we can name them now. So we gotta say P1, P2, all the way up to P sub k, where k is some natural number, which is the largest. It's just indexing the prime number. So if we're saying there's only finitely many, then I can list them out, and the list stops basically, right? So here you go. Here's my list of prime numbers that stop. So the idea is to consider, well, let's multiply all these prime numbers. So now I'm multiplying them, not listing them. And of course, this number is definitely not prime because it's divisible by all the prime numbers. But then if I add 1 to it, then it's not going to be divisible anymore. At least we'll have to show this. But the idea is that it won't be divisible by any of the primes that we previously stated, because if I don't have the +1, then it's divisible by all the primes. But as soon as I add the 1, it should break the fact that it's divisible by any of those other ones, in which case it's not divisible by any of the primes, so it must not be prime, or must be prime itself, and that would give you a new prime, which is not in your list, and that's a contradiction. You said you listed all the primes out, and I give you one more, right? So that's a problem. And the point is that you say, well, okay, we'll add this other one to the list, but then I can do this again, right? As soon as you give me a slightly bigger list, I do this same problem again, you get a contradiction. So this contradiction argument is not dependent on any particular list. It's saying anytime you think you've listed all the primes out, I can give you one more prime number. And so the point is that, and then show that we're going to call this thing capital M, N is not divisible by P1 through pk. And just to see why this is reasonable, let's make a simple table here. So here we'll say if the only primes were, so we're just going to say, we're going to make an assumption, then consider, and then we'll see the contradiction. Okay, so what I'm saying is, let's assume the only primes are 2 and 3. Then we're supposed to consider 2 times 3 plus 1, which is 7, and 7 is a new prime. Right, now that, again, that's too specific, but it's just helpful to see what's going on here. So then let's say 2, 3, and 5 were the only primes. Then we would say, okay, take 2 times 3 times 5 plus 1. If you see what that is, that's 31. And now 31 is a new prime. So notice this, multiply all the primes you assume and then add 1 gives us a new prime, right? Cool. Let's keep doing this because you'll see that sometimes it's a little bit different. So let's say 2, 3, 5, and 7. Then we would look at 2 times 3 times 5 times 7 plus 1. You're going to get 211, and 211 is a new prime. Okay, now let's do the next case. 2, 3, 5, 7, 11. Well, not the next case. I'm going to go a little bit further down. 11, 13, and 17 were the only primes. So then you have to take 2 times 3 times 5 times 7 times 11 times 13 times 17 plus 1, and you get 51, 510,511. Turns out you can write that as 19 times 97 times 277. So it turns out that this number capital N will not always be prime itself, but cannot be divisible by any of the previous primes. And so it will have to be broken down into new primes, right? So now here, 1997 and 277 are new primes. So when I say new primes, I mean ones that I didn't already assume were in my list, right? Okay, so that's an important point. It's not that capital N is going to be prime itself, or I think actually I'm going to call this thing n plus 1 in the proof, so sorry about that. So that'll be n plus 1. So it's not so much that n plus 1, capital N plus 1, is going to be prime itself. It's that it's not going to be divisible by any of the primes in our list, and that will force the fact that it must be divisible by other primes that are not in the list. So either it'll be prime itself or it'll be divisible by other primes that are not in the list. Okay, let's actually look at the proof now that we've gotten some idea for why this makes sense. Okay, so assume, for sake of contradiction, that there are finitely many prime numbers. And so let's let P1, P2, all the way up to Pk, where k is some natural number, be the complete list of primes. And define capital N to be the product of the primes in our list, and we will show that capital M plus 1 is not divisible by any of the primes in our list. Hence, either m plus 1 is a new prime or m plus 1 is divisible by primes not in our list. Either way, that's going to be a contradiction, right? Either I've already found a new prime that's not in our list, or I'm divisible by new primes which are not in the list, and either way, that's a problem. So that's also kind of indicates the two cases that we're going to take here. One is going to be straightforward from the very beginning, and the second will require a little bit of work, right? Because the thing is that, note that either n plus 1 is prime or composite. So this is something we've noticed about natural numbers from the very beginning, that you can you're either prime or you're not prime, which means you're either prime or you're composite. Okay, so case one is that m plus 1 is prime. Well, this one is immediate, right? Um, so since m plus 1 is larger than P1 through Pk, it must be a new prime not in our list, which is a contradiction. Okay. Now, when you're doing a proof by contradiction and then you at some point break into cases, you need a contradiction in both cases, because all we've done so far is shown that if capital N plus 1 is prime, then we get a contradiction. But since that's not the only possibility, for instance, capital N plus 1 could be composite, it's not a complete contradiction for the proof. So now we need to show that both cases lead to a contradiction. So now we need to consider case 2. And if both cases lead to a contradiction, then the entire assumption leads to a contradiction, and we get that the opposite is true, right? So, okay, the case 2 is that m plus 1 is composite. Okay, so we begin by showing that no pi in our list, so that's like for I between 1 and k, can divide m plus 1. Now this gets a little confusing sometimes, but I'm actually going to start another contradiction proof inside of this case. So now I say, for sake of contradiction, assume m plus 1 is divisible by pi for some 1 less than I less than k. Again, I think they do a proof kind of contradiction because in the contradiction hypothesis, I get to assume something I can work with, and that's helpful, right? So that means that then there exists some natural number so that capital M plus 1 is equal to m times pi. Okay, good. But remember that capital N is shorthand for something, right? So that's like saying P1 times P2 times up to Pk is equal to m, sorry, I forgot the plus 1. So plus 1 is equal to m times pi. All right, so now I know that there's two terms in this expression which have a pi in it. There's the m times pi, but then there's also a pi in the product of the primes that make up capital M. So now we want to move things around so that I can exploit this fact. So by moving P1, pk to the right-hand side, we find that 1 is equal to m times pi minus p1 all the way up to pk. Now I know there's a pi in that product, but it's a little bit funny to work with, right? But the way we can write this is I'll pull the pi out because there's a pi in both terms. I'll write it as m minus p1 up to, let me write it first and then I'll show you what it means. So pi with a hat over it up to pk. So this is an important notation that I just want to emphasize. Sometimes in a proof you have to have some ingenuity in the sense of coming up with a proof technique, and then sometimes you have to have some ingenuity as far as figuring out a good way to express something in notation. So this is a scenario where we have some good notation, and let me explain what it means to you and also to the reader, where pi with a hat over it denotes the fact that pi is missing from the product. So the point is, how else do you write the fact that you're still taking the product of all the primes except for pi? Well, this is one way of doing it. It's not the only way, but this is one way of doing it, which is just to say, if I put a hat over it, then it's missing from the product. And the reason why I have to do this is because I don't know which of the primes it is. I don't know if it's the first one, the last one, or somewhere in the middle. So we write it this way. Okay, great. So now notice this is already going to be a problem because we're saying that 1 is equal to the product of a prime times another natural number. And that's a problem unless these things were equal to 1. Okay, so, but pi is not equal to 1 because no prime is equal to 1. And m minus these primes can also not equal 1. You can't take two things that are not equal to 1, subtract them, and get 1. So, well, that's not true, actually. Sorry, you could take 3 minus 2. So we need to kind of like move this around a little bit to see the contradiction. So let's divide both sides by pi. So now, let's write this a little bit differently. So dividing both sides by pi, we find, so we want to find an expression that makes it clear that there's a contradiction, all right? So now we get 1 over pi is equal to m minus this product. Okay, so let's see. Let's stare at it for a second and see if we buy this, right? So first of all, notice that this is actually similar to a contradiction we saw another scenario, right? So since m minus p1 through pi pk is an integer, and now again, that's because we've seen already that if you take products of integers, you get integers. If you subtract integers, you get integers, right? So that has to be an integer. And 1 over pi is not an integer since pi is not equal to 1. Now we really need to say pi is not equal to 1 because if it was 1, then 1 over 1 would be an integer, right? And so, but pi cannot be 1 because it's a prime. Okay, so then that's the contradiction, right? So which is a contradiction. On one side of the equation, I have something which is an integer. On the other side of the equation, I have something which is definitely not an integer, and that's a contradiction. Now, you have to be careful because we have a contradiction inside of a contradiction proof. So what is this a contradiction to, right? Remember, what we assumed was that n plus 1 was divisible by p. So the conclusion we get now is that hence n plus 1 is not divisible by p1 up to pk, since n plus 1 is composite. We saw in theorem 4.8, which is the fundamental theorem of arithmetic, that n plus 1 can be written as a product of primes. So we already proved this fact, which is the fundamental theorem of arithmetic, that every natural number can be broken down into a product of primes. And so as a product of primes, I'll say Q1 now through QL, where L is some natural number. And so m plus 1 is equal to Q1 times QL. Okay, but we know that that it's not divisible by P1 through PK. So since m plus 1 is not divisible by P1 to PK, it must be the case that Q1 up to QL are new primes which are not already in our list, which is a contradiction. Now we've shown that there are two cases in this proof, both lead to a contradiction. So that means that we're done. So therefore, there must be infinitely many primes. Done. Okay, so that was a little bit more of a substantial proof here, the first sort of more complicated proof by contradiction. I hope this made sense to you. And in the next video, we'll look at one more example of a proof by contradiction, which is also famous.